Hello everyone, welcome back to our lectures. My name is Daniel from Huawei Global Training Center. In this chapter, we are going to introduce flink, which integrates stream processing and batch processing in a single engine.
Basically speaking, flink is a stream processing computing engine, but just as the title suggested, flink integrates batch processing and stream processing into just one computing engine. Thus, it can do both offline computing work like log analysis and real-time statistics like page-click analysis. Let's have a short review of last chapter of Spark. In last chapter, we mentioned that Spark is also a one-stop solution for both batch processing and stream processing. Therefore, naturally, we can make a comparison between them. So in Spark, we mentioned a concept called Spark streaming and introduced that Spark streaming is a mini batch processing which simulates stream processing by batch processing. That is, it uses batch processing methods to do stream processing analysis, but it is still a batch processing engine. However, flink is completely on the opposite. Just as mentioned here, flink regards batch processing as a particular case in stream processing. So indeed, it uses stream processing methods to do batch processing tasks. And we say that flink is a pure stream processing engine. So you can tell that how powerful flink is. And next, we are going to introduce how flink works, as well as its architecture and some key concepts, such as the 4 keywords, including state, time, window, and checkpoint. Alright, so the first key concept is state. Here we say flink can do some state management. But you might be wondering, what is state? So the full name of state here is called intermediate computing state. It is an intermediate result when doing statistical computation. For example, when a stream computing system or task is operated for data processing, values obtained from operations such as sum, count, minimum, or maximum need to be stored. These values or variables can be understood as the state because they need to be constantly updated. And below, we mentioned a mechanism for flink. So flink can store states locally instead of storing them in an external system. And we also mentioned several advantages of doing so. And you can just have a look of them if you are interested. Now, let's have a look at the system architecture for flink. And perhaps you may find it familiar to you. So please recall that in last chapter of Spark, we introduced a quite similar graph called Spark Core, right? Remember? So similarly, the architecture of flink could also be divided into 3 layers. The upper layer for different application scenarios, the center layer for runtime, and the bottom layer for different deployment modes. Like Spark, we can deploy flink in a single node system, a cluster, or on the cloud. And different modes require different tools for resource allocation as well as management. As for the central part, runtime, it is the core engine for flink. And we said that flink supports both batch and stream processing jobs. And actually, flink just uses this runtime to deal with all the tasks. So again, that is why we say flink integrates batch processing and stream processing into just one computing engine. And above it, we can see 2 sets of APIs. Literally, the DataStream API is used for stream processing, and the DataSet API is used for batch processing. Different APIs provide services for different tasks, which has been shown here. But please pay attention to the table API and SQL, so you might have found out that both API supports table API and SQL to deal with relational data. This is because data streams can be abstracted into unbounded tables, and data batches can be abstracted into normal bounded tables. And please recall that in Spark, we mentioned Spark SQL, and actually, this table API is very similar as Spark SQL. Next, the data stream. So this data stream is actually the data structure of flink jobs. You can regard it as a data collection which allows duplications, just like an array or a list, but with infinite length. And this graph tells us that we can use various kinds of operators to transfer data streams into some other types, and thus we can do data analysis more conveniently. Typical operators include reduce, window, join, sum, maximum, minimum, you name it. So if you are interested in this, please have a look at them in details. Okay, now maybe you are wondering, what does a typical flink program look like? Here, we introduced that a flink program contains 3 parts: source, transformation, and sink. As suggested by their names, source contains some operators to read data from external data sources. And transform or transformation is responsible for data transformation operations just as shown in that graph. Sync is responsible for final data outputs. Okay, so just now we mentioned that a Flink project includes 3 parts, and the first part is source. So where does Flink read data? Actually, there is no such a strict difference between batch and stream processing. Here, we just suggest several classical usage. So for batch processing, typically we read data in different formats of files. On top of that, it can also read data from relational databases through this JDBC interface, or read data from HBase and some other data collections like arrays or lists or even tuples. As for stream processing, basically it can still read data in different formats of files, or you can use socket streams, Kafka, RabbitMQ, or Flume for data transmission, or even deploy some data sources on your own. This diagram shows us the running diagram for Flink jobs, and in this graph, the key point is that Flink also has some master and slave architecture, so we can deploy HA mode to improve reliability. And now, the job manager is the master node who takes charge of various task managers as slave nodes here. And the Flink program is divided into different tasks, which can be run concurrently in different task slots provided by task managers. As for the running processes, let's see more details here. In this flowchart, the user submits jobs into the client, and the client is just a bridge between users and job manager. It mainly receives, parses, and optimizes program execution plans and submits the plans to job manager. After receiving it, job manager returns a message of program submitted to job client, and meanwhile, it submits the tasks to task managers. And then, the task manager will regularly report the task status back to job manager, and then job manager returns the task results to job client to all the users. And this page shows us the difference between unbounded stream and bounded stream. Just as suggested by their names, unbounded data stream has no lower bound, and we say it has infinite length, while bounded stream has both upper bound and lower bound, which suggests that its length is finite and we can use batch processing method to deal with it. Generally speaking, bounded stream is easier to be analyzed because it has finite length, so we can define a global window as shown in the example here. In this example, we just count the numbers of visitors for each region. Because we make analysis in each hour, we can define a global window just with 1 hour window length. By doing so, all the data are included in the global window, and we just need to add up all the number of visits as the count. Here is another bounded stream case. Different from the former case, in this case, we don't know the length we should define for windows, but we are sure that the data is finite and there is definitely an end of the stream at some time. Therefore, we can define a trigger to shut down the global window according to some algorithms. Or equivalently, use group by instead of key by. As group by is a common batch processing method which will not be triggered until all the data being read are executed by the computing engine. So from this example, maybe you would prefer the second method here, but basically speaking, the first piece of code is more general. But in this case, you can get same results from both methods. Next, let's have a look at the Flink processing model. We just mentioned it before, let's review it now. So just as mentioned, Flink uses the same engine to support both batch processing and stream processing. And we call the engine runtime, right? And different sets of APIs have different responsibility, remember? The DataStream API is used for stream processing, and DataSet API is used for batch processing. To be more specific, DataStream API supports the following mechanisms, including checkpoints, state management, watermark, window, and even trigger. Meanwhile, DataSet API supports the following mechanisms, including backtracking for scheduling and recovery, special memory data structures, and query optimization, all of which are typical batch processing methods in most cases. However, although Flink uses the same engine to support both stream processing and batch processing, still we cannot combine them together because the two sets of API are different. But there is only one exception, the table API and SQL. Just as mentioned before, they are supported by both mechanisms, which means that relational APIs execute queries with the same semantics and produce the same results on unbounded and bounded data streams. This is the only exception for Flink.
Okay, up to now, we have finished the first section about the basic principles and architecture of Flink. Next, in the second section, we can have a look at the time and window mechanism for Flink together.